everyone, I'm Caroline. Today's lesson will be a meteorology lesson, and specifically today we will be focusing on density altitude. So, does anyone know what is density altitude? Okay, you know what altitude is, but if we look at what the books say that density altitude is pressure altitude which is corrected for non-standard temperature. Now you're probably wondering, well, what on earth is that? Okay, so when we're talking about density altitude, we are referring to air density and how it's going to affect our aircraft performance. So air density is the amount of molecules or the mass of air molecules contained in a specific space of air. It is measured in grams per cubic meters, and according to ISA it is 1225 grams per cubic meter. Factors which affect density: we have temperature, pressure, altitude and latitude, and of course humidity. So if we look at the first one, pressure. As you should know, the highest pressure that we have is at mean sea level. So if we look at the picture, our largest column of air, which poses the most amount of weight, occurs at sea level. The higher up we go in altitude, the column gets shorter and therefore there is less pressure. So the higher we go in altitude, the lower the pressure, and as a result the density will be lower. How this lower pressure affects us: it reduces our engine performance and we have reduced lift. Then we go on to temperature. Temperature works slightly differently to pressure in the sense that the density is inversely proportional to the temperature. The higher the temperature, the lower the density. This is because at high temperatures our air molecules spread out, so the air becomes less dense. However, at colder temperatures our molecules all gather together and we have higher density. They are more tightly packed at colder temperatures. So remember, at high temperatures our aircraft performance is going to be reduced. Then we've mentioned altitude already. So as we know, the higher up we go in altitude, the pressure is decreasing. But on our last slide on temperature, we saw that as the temperature gets colder, the density should decrease. So now we have a contradiction, because with pressure our density decreases with altitude, whereas now, as we know, with temperature and an altitude, the temperature decreases the higher up we go, so theoretically our density should be increasing the higher up we go. So what actually happens to the overall density if this is what is occurring? So the density actually decreases at a slower rate with an increase in altitude. The overall effect is actually that the pressure decrease is more dominant than the temperature. So it will have a greater impact than the temperature decrease. That's why the pressure is more significant. If we look at latitude, we have two conditions that exist with latitude, in the sense that closer to the surface, the density increases with latitude. So in other words, the further to the North Pole we go, the density is going to increase. At the North Pole, as we know, we'll find the lowest temperatures and therefore the highest pressures. At the equator, on the other hand, we have high temperatures and low pressures. Then we have the case of we are climbing up higher in altitude. now things change. At higher altitudes, the density decreases with the latitude. So we'll have the lowest density over the poles and the highest density at the equator. Then our final factor is humidity. So remember that water vapor is a gas. So we have water vapor molecules in the air. So in dry air, our air consists of mostly just air molecules, which are tightly packed, and therefore we have greater density. However, in humid conditions, we now have water vapor molecules interspersed amongst our air molecules. These take up the space and cause the air molecules to spread apart, which will result in lower density. So, does anyone know why we need to calculate density altitude? As you know, aircraft instruments are calibrated according to ISA conditions. So any deviation in excess of ISA particularly will result in a reduced aircraft performance. The aircraft will perform as though it is at a higher altitude than it actually is. We will have reduced thrust. Our climb performance is going to decrease significantly. We will have a longer takeoff roll, and we will have a longer landing distance too. Most significantly, we will have a reduced allowable mass. So even though our aircraft manual states we can take maximum all-up weight of a certain figure, this will not apply because our aircraft is actually performing at a higher altitude. So we will have to reduce our aircraft mass and obviously our payload. So if we take an example, this is OR Tambo Airport in Johannesburg, South Africa. This is a high altitude airport with an elevation of 5,558 feet. So before we even begin to climb, we already have an elevation of 5,558. If we look at a particular condition for the day, we will select an outside air temperature of 36 degrees, not uncommon in the middle of summer, our QNH 1023, and we have a high humidity. So, how do we calculate what the density altitude will be? This is the quickest way to calculate this. So, our density altitude will be equivalent to the pressure altitude added to the temperature deviation multiplied by 120. I am assuming that a lot of you have forgotten how to calculate all of this, so I will take you through a process so we can get the figures in order to calculate this. If you remember the word plasmas, it will help you go through the process of this calculation. So, the first thing we will do is we will calculate our pressure altitude. In this case, our local QNH is 1023. We subtract the standard from this to get a difference of 10 hectopascals, and we multiply by 30 feet. If in the exam you're given 27 feet, then obviously you would use 27 feet. But rough average is 30 feet, which will give us an answer of 30 feet. This is the difference in pressure. If the QNH is higher than 1013, we will subtract the difference from the actual altitude. So we will round our figure off to 5,500, subtract 300, which gives us 5,200 feet. In the case that the standard of 1013 is actually higher than our local QNH, then we would add the difference. Okay, then we need to work on the lapse rate. So now we want to try and work out what is the temperature according to ISO conditions at 5,000 feet. So as we know, the temperature is reducing by 1.98, or rounded to 2 degrees per 1,000 feet. So if we multiply 5,000 by minus 2 per 1,000 feet, that gives us minus 10. We now need to add this to ISO so that we know what the ISO temperature is. So minus 10 plus 15 degrees gives us plus 5 degrees. This is the ISO standard temperature at 5,000 feet. Now we want to work out the temperature deviation between what we have and the ISO standard. So our current outside air temperature at Johannesburg Airport is plus 36 degrees, and we subtract plus 5 degrees in order to get a temperature deviation of plus 31 degrees. Now, in order to get the equivalent in feet, we will multiply this by 120. So 31 multiplied by 120 will give us a difference of 3,720 feet. Now, if the current outside air temperature is higher, this will always be detrimental to our flying conditions. So we will add the 3,720 to our original pressure altitude of 5,200 feet, which gives us an answer of 8,920 feet as our density altitude. In the case where our temperature is actually lower than the ISO, then you would subtract it. As I said, colder temperature is likely to be less detrimental. So going back to our quick calculation, we now know what our pressure altitude is, we now know what our temperature deviation is, and it's much quicker to calculate. So we'll take 5,200 added to our temperature deviation multiplied by 120 to give us the answer of 8,920 feet density altitude. So if we go back to our airport, as you can see, remember our elevation is 5,558. So if we are loading our aircraft according to the maximum all-up weight, which should normally be fine for that altitude, we're going to have a problem because our density altitude is 8,920. This is a significant difference and will certainly affect our aircraft performance. So, here is the caution. If your airport is hot, if it is humid, at a high altitude, and your aircraft is heavy, these are all warning signs that you need to check your density altitude against the aircraft's performance graphs. And that concludes our lesson on density altitude. Thank you.